Welcome to the deep dive. We're here to take those tricky architectural concepts and make them really clear, stuff you can actually use. So picture this. You built a server, it works great, you test it, handles maybe 1,000 users, no problem. Then you go live.
The big moment.
Exactly. And suddenly you hit, say, 10,000 users, and boom, everything grinds to a halt. It's slow, unresponsive, and you think, okay, hardware, right, add more cores.
Yeah, that feels intuitive.
But it doesn't help, or barely. You're just stuck. Why does that happen?
That's like the classic problem. It used to be called the C10K problem, handling 10,000 connections. And for self-taught programmers especially, it's easy to miss this. The issue usually isn't your specific code logic.
Okay.
It's more about how the whole environment you chose, the language, its runtime, its concurrency approach, how that manages the operating system's resources, the heavy lifting.
Okay, so that's our mission for this deep dive. Let's unpack that. We need to figure out why things fall apart, look at the older solutions that maybe didn't quite cut it, and then really compare the big four philosophies today: C++, Java, Rust, and Golang. The goal is you walk away knowing which tool might be the right fit for your situation.
Definitely. And to get there, we kind of have to go back to the beginning. Why did we even need concurrency in the first place?
Yeah.
Years ago, there was this thing called the memory wall.
The memory wall.
Yeah. Basically, CPUs got incredibly fast, like exponentially faster. But getting data from memory, or worse, from disk or network, that I/O part, it only got a little bit faster kind of linearly.
So a huge mismatch in speed.
Massive. And early servers, they were like a digital waiter, one thread doing one thing at a time. If that thread needed data from a slow disk,
The whole thing just stops, waits.
exactly. The CPU, capable of billions of operations a second, literally sits there idle for milliseconds, just waiting. Total waste.
Okay, catastrophic waste.
Yeah.
So concurrency, doing multiple things, or at least making progress on multiple things, was the obvious answer.
It is the only way forward.
Yeah.
Structure the work so the CPU can switch to task B while task A is off waiting for that slow I/O.
Sounds great on paper, but then
Yeah.
chaos, right?
Hmm?
Suddenly you have multiple threads trying to use the same piece of memory. Race conditions. How does that even happen with something simple like adding one to a counter? Isn't that like atomic?
You'd think so, but no. Even counter plus plus A, that looks like one step. To the machine, it's usually three. Read the current value, add one in a temporary spot like a register, then write the new value back. So if thread A reads the value 5 and then thread B reads 5 before thread A writes back 6,
We both try to write back 6.
right? One of the increments just vanishes. Poof, data corrupted instantly.
Okay, that's bad. So programmers figured this out and added locks, mutexes to protect those critical sections.
Mutual exclusion, only one thread in that sensitive area at a time. But then you get the other big headache, deadlocks.
Oh, right. Thread A locks resource 1 and needs resource 2. Thread B locks resource 2 and needs resource 1.
And they both wait forever. Frozen server. Again.
So we fixed the waiting on hardware problem, but created these really subtle, hard-to-find software bugs.
Exactly. We needed a better way, a reliable way to make progress without freezing or scrambling data.
Okay, so what was the first sort of mainstream attempt? The thread per connection idea seems simplest. New connection comes in, start a new OS thread.
It is the most intuitive. You write your code like it's just handling one user sequentially and let the operating system juggle the threads. Simple to write.
But that's what breaks at C10K, right?
That's at the breaking point because OS threads are heavy. We're talking megabytes of stack space, kernel resources. They're not cheap. But the real killer isn't even the memory.
It's the switching.
It's the context switching overhead. The kernel has to constantly pause thread A, save everything about its current state registers, cache stuff where it was in the code.
Like hitting pause and saving the game state.
A very detailed save state. Then it has to load thread B's entire save state. When you have thousands or tens of thousands of threads doing this constantly.
The system spends all its time just managing the threads, not running my actual application.
Precisely. Performance just tanks because of pure overhead. The system is busier shuffling papers than doing work.
Okay, that makes sense. Creating threads is expensive. Running too many is expensive. So the thread pool, obvious optimization, reuse threads, have a fixed number.
Yeah, amortize that creation instruction cost. Keep maybe, 8, 16, some number of worker threads ready.
That feels like it should solve it. Why didn't everyone just standardize on that? Why isn't that the end of the story?
Because while it helps manage the threads, it doesn't fix the fundamental problem of blocking I/O. Imagine your pool has, say, 16 threads. if all 16 happen to pick up tasks that need to query a really slow database.
All 16 get stuck waiting.
Exactly. The pool is full of blocked threads. No thread is available to pick up new incoming requests. We call it thread starvation. Requests pile up, users see timeouts, and your server is effectively down again.
So even with pooling, blocking is still the enemy. Which leads us, I guess, to the big paradigm shift. Asynchronous, event-driven stuff.
Right, the core idea flips.
That-
Stop waiting, start initiating.
Okay, explain that. The master chef analogy you mentioned.
Yeah, think of a single, super efficient chef. They don't stand there watching one pot boil. They put something in the oven that's like starting a non-blocking I/O request, maybe a network call. They set a timer, the callback, and immediately turn to chop vegetables for the next order.
They don't wait for the oven. They rely on the timer, the event, to tell them when it's done.
Exactly. Maximize productive time for that one worker. They're always doing something useful, not just waiting.
And the OS helps here, right? Things like epoll on Linux. That's the magic.
That's a huge part of the magic, yes. Epoll, kqueue on BSD macOS, IOCP on Windows. These APIs let a single thread efficiently monitor thousands of I/O sources, network sockets, files, whatever.
Efficiently how?
Without having to ask each one, are you ready yet? The OS just tells the thread when one is ready. And checking this is incredibly fast, basically constant time, or wonder how many connections you have. That's where the massive scalability comes from.
Wow, okay. So one thread can handle tons of connections, but there's got to be a catch.
Oh, there are catches, big ones. First, if that single event loop thread gets stuck on a long CPU-bound task like some complex calculation, not I/O.
It blocks everything else
Yeah,
because there's only one chef.
precisely. The whole server freezes. No other I/O events get processed. And second, the programming model gets tricky.
Callback hell.
That's the classic complaint. Managing state across all these asynchronous calls, passing data around, it can become a real tangle. Debugging is harder, it's powerful, but complex.
So the early solutions traded one kind of problem for another, which sets the stage for how modern languages decided to tackle this whole concurrency mess. Let's get into the 4 big philosophies we see today.
Sounds good. Let's start with the old guard, in a way, CC++EO. The philosophy here is basically explicit control, maximum power, minimum hand-holding.
Closest to the metal, you want performance, you manage the OS threads yourself, std.thread. You handle the locks, std.lockguard, hopefully.
Right. You pay for exactly what you use, nothing more. The performance potential is, well, unmatched. Think high-frequency trading, game engines, scientific computing, anywhere raw speed is king.
But the cost, the tax you pay seems huge. You're juggling manual memory management and manual locking.
Yeah.
Getting that right, especially avoiding data races, isn't that incredibly difficult?
It's the highest difficulty level, yeah. Debugging concurrency bugs in C++ can be an absolute nightmare because they might only show up under specific timing conditions. You rely heavily on discipline and tools like RAI wrappers to even have a chance of making it safe. You trade ease and safety for that ultimate speed and control.
Okay, so that's one extreme. What's the counterpoint? Maybe Java.
Good transition. If C++ is explicit control, Java's philosophy is managed abstraction. Safety and developer productivity come first, enabled by the Java virtual machine, the JVM.
Right, the JVM takes a lot of burden off the programmer.
Okay.
Garbage collection handles memory, which eliminates a whole class of bugs right there, especially tricky ones involving memory lifetimes across threads.
Exactly. And you don't usually fiddle with raw threads. You use higher level concepts like the executor service framework. It handles the thread pooling, task submission, all that complexity for you.
Plus, things like semaphores, countdown latches, more tools to help coordinate threads safely, and the Java memory model, the JMM.
Crucial. The JMM provides formal guarantees about when writes made by one thread become visible to others. It gives you predictability, which is essential for writing correct concurrent code. Java's great for large, complex enterprise systems where you have big teams and reliability is key.
But there's still a tax, right?
Mhm.
The JVM itself adds overhead. And garbage collection. Even with modern GCs being amazing, they can still introduce pauses, right? Little unpredictable latency spikes.
That's the trade-off. You get safety and productivity, but you give up some control over raw performance and absolute latency determinism. Those GC pauses can be an issue for certain very low latency applications, though they're much less of a problem than they used to be.
Okay, so C++ is raw speed control. Java is safety productivity via runtime management. Where does Rust fit in? It feels like it tries to bridge that gap.
That's exactly what Rust aims for. Its philosophy is fearless concurrency. The goal is C++ levels of performance without needing a garbage collector and guaranteeing memory safety and preventing data races at compile time.
Okay, hold on. Preventing data races at compile time. How?
Through its core features, ownership and borrowing. The compiler enforces strict rules about who owns data and how it can be accessed. Basically, you can have one mutable reference, allowing changes, or multiple immutable references, read-only, but never both at the same time.
So the compiler itself stops you from creating situations where two threads could write to the same thing simultaneously.
Precisely. And it uses traits called send and sync to check if types are safe to transfer across threads or be accessed by multiple threads. If your Rust code compiles, it's generally free from data races. It's a huge guarantee.
Wow, that sounds amazing. What's the catch? Because there's always a catch.
The catch is the learning curve. It's steep. You spend a lot of time, especially initially, fighting the bar checker. The compiler is very strict, and you have to learn to think in its terms about lifetimes and ownership.
So you pay the complexity cost up front during development, arguing with the compiler.
Instead of paying it later, debugging mysterious crashes in production at 3 a.m. It's a different kind of tax cognitive load and initial development time traded for runtime safety and performance.
Right. Front-loading the pain for long-term gain. Okay, that makes sense. And the final one, Golang. Go seems to take a completely different path again.
It really does. Go's philosophy comes from a different model called Communicating Sequential Processes, CSP. Their famous mantra is, do not communicate by sharing memory. Instead, share memory by communicating.
Okay, unpack that. Share memory by communicating.
Instead of multiple threads using locks to safely access the same piece of data, sharing memory, Book encourages you to have one piece of data owned by one routine. And if other routines need to interact with it, they send messages to that owner over a dedicated conduit.
Ah, like setting requests instead of directly touching the data. And these routines and conduits are...
Goroutines and channels. Goroutines are the key innovation. They're not OS threads. They're incredibly lightweight, managed entirely by the Go runtime. Think thousands, even millions on a single machine.
Millions. How?
Tiny stacks, just a few kilobytes to start. OS threads have megabyte stacks. This means you can have vast numbers of goroutines waiting on I/O without consuming much memory at all, and they communicate using channels, which are like typed pipes for sending data between goroutines.
So Go is optimized for massive I/O concurrency, like handling tons of network connections, web servers, API.
Exactly. It excels there. It's very productive for that kind of work. Plus, it has a built-in race detector you can enable during testing, which is a great practical tool, even if it's not a compile time guarantee like Rust's.
But simplicity can be limiting, right? And what about downsides? Goroutine leaks.
Yeah, that's a potential issue. If a goroutine blocks waiting to send or receive on a channel and nothing ever comes, it just sits there forever, consuming resources a week. And you can definitely create deadlocks with channels if you're not careful about the communication patterns.
Yeah.
You trade lock complexity for channel coordination complexity.
Okay, wow. 4 very different approaches to the same fundamental problem. So for someone listening, trying to pick the right tool, how do they navigate this? What's the compass?
The compass points towards your primary workload. There's no single best language. It's about alignment. Is your application mostly I/O bound, spending its time waiting for networks, databases, disks?
Like most web backends.
Often, yes. In that case, you want low resource overhead per connection and efficient scheduling. That points strongly towards Golang with its Goroutines, or maybe Rust using its asynchronous runtime like kqueue.
Okay. And the flip side, if the app is CPU bound, lots of heavy computation, math, data processing.
Then raw execution speed and fine-grained control over parallelism become critical. You want to saturate those CTU cores, that's where C++ still shines, or standard non-async Rust for its performance without the GC overhead.
It's interesting, too, seeing how they're starting to borrow ideas from each other.
Absolutely. Look at Java's project Loom. They're introducing virtual threads, which are lightweight, runtime-managed threads, very much like Goroutines. It's a clear acknowledgement that the Go model for handling massive I/O concurrency is incredibly effective and now almost a table stakes requirement for modern platforms.
So it boils down to where you want to pay the price. The system's performance and reliability. It's this balance between hardware, runtime costs, and how much complexity you, the developer, have to manage.
That's a great way to put it, which leads to maybe the core strategic choice for a programmer starting a new concurrent project today.
Yeah.
Would you rather deal with the upfront complexity and steep learning curve of something like Rust, paying that cognitive tax to get compile time safety guarantees against race conditions, or
Or Do you prefer the faster development velocity of something like Golang, relying on its simpler model and its runtime race detector to find the bugs later in testing, accepting that some might slip through initially?
Pay now for guaranteed safety later, or speed now and maybe chasing tricky bugs later? That's a fundamental decision every team needs to weigh.